In this video, what we're going to do is we're going to take Laplace's equation, which is a partial differential equation, and we are going to basically approximate the equation. Okay, so what we have is we have a plate. This plate, which we've spoken about in a previous lecture, now it has to have certain dimensions that allow you to grid it up into a square grid. You can't actually put anything into a square grid, but assume that these dimensions allow you to grid this up into a square grid. Okay. Now, one thing that I can never remember how to do is how to label it, but essentially it doesn't matter that much. You can adjust it if necessary. So what we're going to do is we're going to make a square grid. Now what I mean by that is something like this. So say etc. etc. So what I mean by a square grid is that these little grid points or grid elements, they need to be squares, because this was an assumption. Well, actually, it wasn't an assumption that we made, or whether it was or wasn't, it doesn't matter. But for this, they need to be square. So delta x, delta y, because this is an x-axis and this is a y-axis, we need delta x equal to delta y. Okay. Now, what I'm going to do here is, so I need some kind of a grid. So what we're going to do is we're going to approximate the temperature at these internal grid points. But this is what we're going to do. And I think what I want to do is maybe just take a group. We'll grid a little bit more, and we'll look at a point up here. Well, we'll do dot dot dot, as if we've gone on for a while, and then put a square here, and do a dot dot dot, and do another grid here, grid lines. I think I need a few more. Yeah, I need to do a few more, so we'll go up one more. And I need to go over one more. So you have some kind of labeling convention. Okay, so got a temperature here we're going to look at, temperature here we're going to look at, temperature here, here, and here. Right. Now the way I'm going to label this is that we're going to have little... Now the notation is important enough here to follow what's going on, but after that you can actually kind of use your own notation. In this one, look, this is the way we'll do it. We'll say this is 0 times delta x, 1 delta x, 2 delta x, 3, and this will be a general point I delta x. The next point, this refers to this, and because the width is delta x, we know this is I plus 1 delta x, and we know that this is I minus 1 delta x. And similar story, let's take this to be j delta y, so we know that this is j plus 1 delta y, and this is j minus 1 delta y. Okay, and what we're going to do is we are going to, so this particular point, we're going to refer to the temperature at this point as temperature I j, and now I could write that this is equal to the temperature at, you could call this xi yj, but it's actually I times delta x, j times delta y. But this is going to be an approximation, so I'm just going to write this will be an approximation of the temperature at I delta x I delta y. Okay. So in terms, okay, now this might be a little bit confusing. Okay, probably a few things we have not quite mentioned. The first thing is that this is a very thin square plate. It's insulated on top and bottom, and there's boundary temperatures the whole way around. And what we want to find is the steady state equilibrium temperature distribution across the plate. And what we're going to do that is to solve what's called, well, how you do is solve Laplace's equation. And what we're going to do is we're going to approximate Laplace's equation. Okay, so now let's write down a few more things. So this then, in the same notation, is I plus 1 along the x. It's the same y coordinate, so it'll be ti plus 1j. This one over here would be, now this is minus 1 along the x, it's 1 beforehand, but same height. This one has the same x coordinate, so it's ti, but it's 1 up in the y, so it's j plus 1. And then this one is ti, because it's the same distance along the x, and j minus 1 along the y. And so the point I'm actually interested in, the middle point, is Tij. Okay. So this is the setup. Now, as I said later on, and maybe even when we do questions, we'll see, you could, in theory, like for a small grid where maybe there's only maybe 9 internal points, you could call them T1, T2, T3, T4, T5, T6, T7, T8, T9. That's no problem. And this is probably what I'm going to run with. Okay. So we could number the grid points, but it makes more sense to label them. And in particular, this is good if you want to use an array. Okay. So, consider a point where the temperature is denoted by this. Well, this is our approximation to it. Use this approximation. Now, what I actually need to write at this point is Laplace's equation, which describes the temperature distribution when the temperature is in equilibrium. So Laplace's equation says the second derivative of temperature with respect to x plus the second derivative of temperature, partial derivative with respect to y, is equal to 0. And what we're going to do is we're going to approximate both of these second derivatives here. Okay. Now this, you will have to wrap your head around. Once you get it, it is genuinely quite easy. So, this is what's called a finite difference approximation. And what it's saying is that you can approximate a second derivative at a particular point using this. So here is, so y is the function that you're approximating. xi plus 1, maybe we'll just draw a little bit with this. So xi is the point where you're at. Xi plus 1 is the next point. It'll be, that's here. I just want to look at, because, sorry, I can't freeze here, but I've done something a little different to what I normally would do. Apologies for this now. Okay, it's not actually that important. So the bit I'm just worrying myself a bit there is often I have these mixed up, but no, it's okay. So this is the next point, and then this is the previous point. And this is the value of the function at the previous. This is the value of the function at the point you're interested in. This is the value of the function at the next point. Delta x is then the difference, the width of these little things. Okay. Now I'm going to put some English on this now. So in terms of what we're talking about, this here is next. This is current. And this is previous. I don't know if you can see this or not, but you can hear me say it. So this is the value of the function at the next point minus twice the value of the function at the current point plus the value of the function at the previous point. And you get this line. So next, current, previous. And now what we're going to do is we're going to use this approximation of the second derivative to approximate this second derivative and also this second derivative. Now what you have to understand is this is a partial derivative. So this is changing along the x. Maybe I'll put a bit of green in this. And this is a partial, so what that means is x is changing but y is constant. So it's not like it's going in a funny direction, it's going straight across. So if we're talking about this point as we were, this will be the temperature current, this will be temperature next in the sense of x, and this will be temperature previous in the sense of x. And it's a partial derivative, which means that you don't change along the y. You stay at j delta y, you just move along this axis. And similar story, this just moves along the y-axis. Okay. So now what we're going to do is we're going to approximate this partial differential equation using this. So what we're actually doing here in the first place is, rather than taking an equation and directly finding approximations of solutions to the equation, we're actually going to approximate the equation itself. So it's slightly different to what we've done before. There is a different type. Well, it's a different story. With a pendulum, there's a sine theta term, and what you do with that is you, if the angle is kept small, so this is a small oscillating pendulum, sine theta is approximately theta, and so what you do is you approximate the equation and then solve the equation exactly. We can do something similar here. You can approximate the equation and solve it exactly. We're actually going to approximate the equation by easier equations and then actually approximate solutions to those easier equations. So there's a double approximation. The second one isn't too bad though. Okay, so let's do this. So we're going to do the second derivative of, now I'm going way over left here, the second derivative of temperature with respect to distance plus the second derivative of temperature with respect to vertical distance, this is horizontal distance. And now this is equal to 0, but we're going to approximate this. Okay, so we're going to use this thing here. Next current and previous with respect to x, and we're evaluating this, we may as well say here, at the point given by I could say I delta x, sorry, this should say j actually, j delta y. I'm going to call this xi and this yj. So we're approximating at xi yj. Okay, so in terms of x, the next temperature in terms of x from here, because that's the point where we are, is this one. This is the temperature at the next point. So this is T subscript I plus 1 comma j. So this is the next temperature in terms of x, minus twice the current temperature. That's the temperature where we are, which is just ij, plus the temperature at the previous point in terms of x. So the previous point in terms of x is this one, Ti minus 1j, divided by delta x squared. Now, if I give you the dimensions of the plate and say the dimensions of the plate are, say, 60 centimeters, and you take, say it's 60 centimeters by 60 centimeters, and you take, I ask for a 3 by 3 grid, then delta x would be 20 centimeters. But this one is just abstract. Okay, so that's the approximation of the second derivative with respect to x. What about the approximation of the second derivative with respect to y? So here, when we're going with respect to y, this is the current next previous. Current next, excuse me, current next previous. Current next previous. Okay, so the next temperature in the sense of y is up here, Ti j plus 1, minus twice the current, which is 2 Ti j, plus the previous, which is down below here in the sense of y, plus Ti j minus 1, all divided by delta y squared. This is an approximation to the sum of those two partial derivatives. Those two partial derivatives equal 0, so therefore this is approximately equal to 0. Well, we'll just say equal to 0. I suppose it's really approximately. Okay. Now, if you make some assumptions, in particular, if you assume that you have a square grid, delta x equal to delta y, you can multiply both sides by delta x squared, which is the same as delta y squared, and you will end up with this little equation here. For example, so this is saying, e.g. at x1, y1. You end up with this. Okay. What do I want to say here? Okay, I want to say nothing at the moment. Okay, if you actually write out the linear system, so basically what you have is, let us say, for each point in the grid, you get an equation. So each grid point, internal grid point, gives you an equation. Right. Now it's telling us something about a diagonally dominant system. Right. See, can I actually remember this? So what you end up with, if I am remembering this correctly, is something like this. Something like this. So you end up with, say, the first equation, if you write it out, you'll have a 4 here, and then, so take these away from both sides, you'll have minus 1s in the other places. I'm just a bit concerned about this being equal to 0. Oh yeah, okay. So the thing that we're missing is the boundary temperatures. So some of these things are known. So for example, T01 would be, we'll just write it up on this thing. This would be 0 along the x, 1 along the y, that's up here. And that would actually be a known value that you would be told, oh, the temperature in this boundary is whatever. I also see a T10, that's 1 along the x, 0 along the y, that's down here. So they'll be numbers that you know. Okay, so some of these, the constants will be 0. For the ones that are really internal, the constant will be 0, but the others, there'll be numbers. So you end up with something like this. So there'll be a 4 along all of the diagonals. And then up to 3 minus 1s in the other places, but we won't worry about that. There'll be a vector of temperatures here, and then equal to some constants. Okay, but now the issue here is I've actually cut some of the material in the manual, and this would have been touched previously. But anyway, so basically what happens here is you end up with diagonally dominant. And what diagonally dominant is, it says that when the number on the diagonal, when the absolute value of that is greater than the sum of the absolute values of all the other things, you've got a diagonally dominant system, and that means it's really, really well behaved. It has a unique solution. I don't know if you learnt about infinite solutions and no solutions when you did linear algebra, but in this case you have a unique solution, and something called the Jacobi method and Gauss-Seidel method, which I know you have done with Bob, will work. Okay, so I'm just going to say that the linear system, because we got at each grid point you've got an equation. So say, for argument's sake, there's 9 internal grid points, you have 9 equations and 9 unknowns. Now that's a problem because it's difficult to solve that. We've mentioned this already, but because it's diagonally dominant, and let's just say this is nice, it's easy to approximate the solutions. Okay, now how you approximate the solutions for a diagonally dominant, how you do Jacobi and Gauss-Seidel. Now Bob has done it in kind of great depth last semester. I'm a little bit more focused on the applications, so I'm going to give you a slightly easier way of doing the Jacobi method and Gauss-Seidel method than what Bob did. So what you have to do, the easy way of doing Jacobi and Gauss-Seidel, is you solve for the dominant equation. Excuse me, the dominant variable. So the dominant variable is the variable along the diagonal. So in this is the dominant, and this is the dominant. And what you do is you solve for this. So say here, you'll add this to both sides, divide both sides by 4. Here you'll divide both sides by 4. And what you get is something slightly different to what we said each grid point gives you an equation, but now each grid point, say ij, gives you an equation for the temperature at that point. So as you go through, so at each point you're going to approximate Laplace's equation, and the approximation of Laplace's equation at that point is going to be your equation for the temperature at that point. Now we will see examples, so bear with me until then. So as I said, such systems can be solved using the Jacobi or Gauss-Seidel method. So what you do is you solve for Tij. So if I'm going back to equation 2.2 on the previous page, I end up with Tij equal to, and what you end up with, we'll show what this means. So if I'm looking at equation 2.2, I get Ti plus 1j plus Ti minus 1j plus Tij plus 1 plus Tij minus 1 divided by 4. Now this means that you don't actually have to remember 2.2. You don't actually have to derive 2.2. You can just write down these equations, because look at what this is. The temperature at a point. Now let's look at these temperatures on the grid. So it's saying the temperature at this point, those 4 temperatures are the ones around it. The temperature here is the average of those 4 is what this thing says. And for Laplace's equation, that's actually all you're going to have to do. Well, we'll see. So we end up with, you just have to write down the temperature at a certain point. So Tij is equal to the average of the adjacents. And when I say adjacents, I mean adjacent temperature. Now, one small thing. See this thing, they're not adjacent. It's only the ones that are the same, equal distance away. Okay. Let me see. What else do I need to say at this point? Okay, I said this is the only thing you have to do. If I give you a plate and I ask you to approximate the equilibrium steady state temperature distribution, this is all you have to do. But there are other theoretical questions we might be interested in that we're going to do in the next video. Okay. So this is exactly the form these equations need to be put into to implement Jacobi or Gauss-Seidel. Now we're probably going to see the Jacobi and Gauss-Seidel methods in, you're going to see it in the lab where it's actually very easy, but we will also have an examples video. Now there's something called relaxation factors that can speed up the convergence. So basically what you can get with these methods is that it's going to be an iterative method. We will see this in the example, but the iterative method, it can kind of overshoot. So say, let me put it this way. Imagine it like a swing and you're trying to get to the vertical. These things tend to overshoot and to kind of oscillate around the exact solution. And what you can do is do a relaxation factor. That means it doesn't move so much. So it'll either, if you're trying to get to the middle, it'll overshoot but make the overshoot smaller, or it won't even overshoot at all. It kind of well, they're called relaxation factors. It just kind of slows things down. You can almost think of them as some kind of abstract damping of the solutions. Right. Now, you do not have to use these. You don't have to. It just speeds things up a little bit. And when you do the labs, you'll be invited to use, for example, this relaxation factor, but you don't have to. Okay. Now there's these 2 methods. We will talk about them in a later video. Gauss-Seidel and Jacobi. Gauss-Seidel is really the one you want to do. It's much easier altogether. Okay. So what we're going to say next in the next video is that these equations that so you grid this plate up into a square grid in the sense that each of these grid elements are these little area elements or volume elements or whatever you want to call them, they're squares. That for each internal grid point you write down a temperature, that the temperature at the grid point is the average of the 4 adjacent ones. This is not a mistake, and we'll see this in the next video.